This is recording 1A in a series on working with radicals for Section 5-1 of Unit 5, Chapter 5, Mathematics 2200. We'll focus our attention here on reviewing the radicals and rational exponents work that was done in Mathematics 1201. Parts of a radical. You have here an index inside the little v part of what's called the radical symbol or radical sign. And under the radical sign is what we call the radicand. So for square roots, though, there's a special case. The index is not normally written, but the index is understood to be 2. For example, square root of 8, we could write it with the index 2 if we desired. Some review of perfect roots. Some of the more common ones you'll need. For example, the square root of 4 is 2. Square root of 9 is 3. And I'll write that little index in. Square root of 9 equals 3. Because 3 squared equals 9. That exponent has to match the index. So down to the perfect cube roots. The cube root of 8 is equal to 2. Because 2 cubed, which is equal to 2 times 2 times 2, is 8. On the other hand, the cube root of negative 8 equals negative 2, because negative 2 exponent 3 equals negative 2 times negative 2 times negative 2, which gives us negative 8. Notice the odd number of negatives here. So when you have an odd index, you can have a negative radicand. If you have an even index, you cannot have a negative radicand. So I've written that conclusion up here for you. If the radical has an even index, the radicand cannot be negative. So it would be good for you to complete some of these, some of the values here on this number line. 0 is the 4th root of 0. 1 is the 4th root of 1. 2 is the 4th root of 16, because 2 to the 4 is 16. 3 is the 4th root of 81, etc. Okay, 4th root of 81, 3 to the 4 is 81, so 4th root of 81 is 3. You should do some of the common 5th roots as well, such as 5th root of 32 is 2. The 5th root of 243 would be 3. Also remember, you can have negative radicands when you are doing 5th roots because you have an odd index. Now we need to use that for converting, or those ideas for converting radicals to simplest form mixed radicals with the smallest possible radicand. This one is the square root, so we need the largest perfect square root that divides into the square root of 48. Going back to our square root number line, square root of 4 will divide into the square root of 48, but so will the square root of 16, so we'll use that one, that's larger. So our largest perfect square root that divides into the square root of 48 is root 16, therefore we have root 48 equals root 16 times root 3, because 16 times 3 makes 48. Square root of 16 is perfect, square root of 3 is not. So likewise, the largest perfect 4th root, because our index is 4, that divides into the 4th root of 324 is the 4th root of 81. So we express this as, or express the 4th root of 324 as the 4th root of 81 times the 4th root of 4, because 81 times 4 is 324. The 4th root of 81 is 3. 4th root of 4 is not perfect. For this next one, we note that the index is odd. It's a cube root. And we have a radicand that's negative. So we look for the largest negative perfect cube root that divides into the cube root of negative 56. Let's go back and have a look. Cube roots. The largest negative perfect cube root that would divide into negative 56 would be negative 8. Cube root of negative 8. So we will use the cube root of -8 and express the cube root of -56 as the cube root of -8 times the cube root of -7, no, +7 rather, and that gives us -2 cube root of 7. Next, we sometimes want to go from the mixed radical to the entire radical. To do that, we first consider what the coefficient is. In this case, it's 4. And then we have to raise that coefficient to the same exponent as the index before placing it under the radical symbol. So we have here square root. Remember, the index is 2 here. So we've got the square root of 4 squared times 5. So the index has been raised to the power of 2. And that gives us a total of the square root of 16 times 5 is 80. In the next one, the coefficient is -2. So we raise the -2 to a 3 because that's the index, times 5. And we have -8 times 5, which gives us the cube root of -40. For our last item of review, we look at rational exponents. The cubed root of b is equal to b to the 1 over q. So in other words, the cube root of 5, for example, would be equal to 5 exponent 1/3. If we have an exponent on the radicand, then that exponent becomes the numerator in the radical. So example 5, cube root of 5 squared would be 5 to the 2/3. In conclusion, know the parts of a radical. A perfect root, such as a cube root, is one in which the radicand can be expressed as a power of the index, like so. Radicals which are non-perfect can often be expressed as mixed radicals by first expressing the radicand as the product of a perfect radical and a non-perfect radical. And radicals can be expressed using rational exponents.